Thanks. So ocean and sea ice reanalyses combine dynamical ocean models as well as available observations and surface forcing to produce a regularly gridded historical depiction of the ocean states. So they're very similar to atmospheric reanalyses, except for the ocean. In the Arctic, they have particular challenges associated with sea ice, the sparsity of observations, and other factors that I think we'll discuss. And so we're here to talk about two relatively new products. And we'll begin with Jim Carton. Jim Carton is professor of atmospheric and oceanic science at the University of Maryland at College Park. He's not my advisor, I'm afraid, but he seems to be a lot of others. And he's here to talk to us today about RARE, the Regional Arctic Reanalysis. Jim.
You guys can see that okay?
Yes, and we can hear you. That's good.
Okay. Okay, so this is great. This is my first presentation on this, and I'm here to really try and get feedback. I sent a manuscript to Mike Steele, so Mike's already seen a pre-version of this. But anyway, so RARE is what you might call a conventional ocean reanalysis. The ocean model is MOM5 with SIS version 1 sea ice. It's got relatively fine horizontal resolution. It's between 2 and 5 kilometers. It's about 2.5 kilometers at Fram Strait. It's got 75 vertical levels, so it's 1 meter resolution near surface, and then it telescopes towards the deep ocean. Surface forcing is from ERA 5. River discharge is a gauge-based data set that we put together. As I say, the data assimilation is sequential data assimilation. I'll say a little bit more about that in a moment. That's one of the big differences between the two presentations that you're going to hear. Observations we're taking from the latest releases of the World Ocean Database. We have SST, both satellite and in situ, and we constrain sea ice to be reasonably consistent with biomass. That's the model grid below. It basically describes the ocean poleward of 45 degrees, but the resolution increases as you get into the Arctic. And in order to give you some idea of how much change there is in RARE with respect to the kind of standard global ocean reanalyses, I compared the results here to a version of SODA, which has all the same forcings and slightly different initial conditions, but same data sets, same data assimilation package, and so forth. And the main difference between the two is model resolution. And so one of the points I'm going to make is that model resolution really is something that we need to focus on. Oh, the time period for RARE is 1980 to 2020. We're just waiting a few months and then we'll have 2021. So I've got about 10 slides here and I'll just run through them now. The first couple describe the model system itself and its performance, and then the rest are results. So the data set you're probably familiar with. It's all the collected profile data in World Ocean Database. The data coverage in 1990s is a little bit less than in the 80s, and certainly much less than in the 2000s. And you can see, of course, the data coverage is inhomogeneous. Much of the Central Arctic in the 1990s was data sparse, and of course the shelves are data sparse. And that's just one of the constraints on trying to do data assimilation in the Arctic. The data assimilation used in RARE is the same as the data assimilation used in SODA. So it is sequential. That means that we carry out a series of short forecasts. We compute differences between the observations and the forecast fields. The gridded version of these differences we call the analysis increments. And we collect all that analysis increment data, or if you like, misfit data. And the accumulated misfits tells you a lot about how good your analysis system is, how far off from the observations you are. So just to give you an example of what you can learn from that, these are the time and horizontal average analysis increments coming from rare in black and soda in green as a function of depth. So just to say that again, this is essentially the time mean misfit or bias of the analysis system. And just to make a couple of points, one is that there is a systematic cold bias near surface and fresh bias near surface. And the systematic biases are much lower in rare than they are in this quarter degree global soda reanalysis. And we explain that difference, that reduction of the black curve relative to the green curve as improvement of the modeling system. One more detail, by the way, a lot of the bias is occurring in the summer, and it's occurring in the parts of the ocean that have been recently exposed to the atmosphere. So these are the parts of the ocean where the sea ice is retreated and left very cold water exposed to surface heat flux. So that's where the bias is coming. So the rest of the slides I'm going to show you are results from rare version 1. And the first picture I'll show you is a picture of speed in the left and eddy kinetic energy in the right for the Nordic seas and Barents Sea. So you recognize Greenland and Europe there. And the currents which are flowing northward are colored red. The currents which are flowing southward are colored blue. And if you look at that picture over on the left-hand side, you Arctic oceanographers, you probably recognize everything. You'll see that strong Norwegian coastal current flowing northwards along the margin of the Barents Sea through Fram Strait on the eastern side, the East Greenland current flowing southwards on the western side, the actual splitting of the East Greenland current into a shelf current and an offshore current south of Iceland. So it all looks pretty reasonable. You'll also notice, kinetic energy, I'll come back to that in a moment. You'll also notice that surface salinity increases in the northeastern Nordic seas. That's a result of mixing up of the salty Atlantic water, which is coming in underneath. So it's really an indicator of where there's a lot of turbulent entrainment going on. And you can see why that entrainment is going on if you look at the eddy kinetic energy over on the second slide. Eddy kinetic energy here is defined as the difference between the 5-day velocity and the time mean velocity, zonal component squared, meridional component squared, added together, take the square root. And so where you see the blues and purples, these are all places where there's lots and lots of eddy activity. You see that a lot in the Lofoten Basin around 70 north along these shelf break currents and even extending into the Barents Sea. Oh, interrupt, by the way. I mean, obviously, I'm just going through this. The lower panels show this corresponding pictures for soda. You can see the currents are actually weaker, and sorry about that. Currents are weaker, and the eddy kinetic energy is much weaker. So again, this is a result of the higher resolution model being used in rare now. Now this water which flows north through Fram Strait joins Atlantic water, which has transited the Barents Sea and is flowing northwards through these ice age drainage channels along the northern margin of the Barents Sea. And it all goes into this boundary current, which flows counterclockwise around the interior basin of the Arctic. And so the pictures on the lower part of the slide show cross sections of that boundary current for rare over on the left, for soda over on the right. This section is at 95 east, so it's right there. Just on the eastern side of the Barents Sea, Kara Sea, you guys probably know. Anyhow, you can see substantial differences in the time mean currents along the shelf break. The currents are much more tightly linked to the topography in rare, and they're confined to the water column above 1,000 meters. And the contours show time mean temperature. You can see that the Atlantic water, which is filling that central basin, is pulled in right up to the shelf break. Whereas in soda, that water is displaced offshore. So you have actually rather cold water right along the coast. The coastal current itself is much broader and extends much deeper in the water column. And the depth is a problem because, as you know, there's a lot of topography in the Arctic when you get down to like 1,500 meters. And so if the currents extend too deep, then they start to feel the topography and you get erroneous topographic steering. And you can actually see the effects of that if you take a look at temperature between 200 and 500 meters. So again, rare is on the left, soda is on the right, the high temperature waters in red. And so you can kind of, looking at this picture, you can, and green is the summertime ice edge. And so you can kind of see this Atlantic water making its way into the Amerasian Basin, into the Pacific side of the Arctic along the margin. And it's a little bit different. It plays out somewhat differently in soda. And my impression, and you guys correct me if I'm wrong, is that this is actually a major mechanism by which this Atlantic water is actually moving into that Pacific side of the basin. So you really got to get the current right. Just to entertain those of you who think about the Pacific side of the Arctic, these are the surface currents at Bering Strait. The time mean speed over on the upper left, eddy kinetic energy upper right for rare, and lower left and lower right for soda. And you see the acceleration of the currents as you get into Bering Strait and the strong eddy kinetic energy. You can see I guess this is the Chukchi shelf current here, which is rather evident in rare, less evident in soda. Mixed layer depth. This is something I know Mike is interested in. So the upper panel shows the climatological March and September mixed layers in rare, middle panel soda, lower panel I put in Ian for just because if we were mid-latitude oceanographers, we'd want to do our comparisons to something like EN4. And you see, I think many of the features that you expect to see, you see these very deep winter-spring mixed layers in the Greenland gyre, very shallow mixed layers under the really thickest part of the Arctic sea ice. In winter, the mixed layers get much, much shallower in summer. I assume this is because of the ice melt, making that really shallow halocline. One difference between rare and soda is that the mixed layers in winter are shallower. So the season when the mixed layers are deep, they're actually shallower. In the season when they're shallow, they're actually a little bit deeper. And then you can see some of the funny aspects of EN4 here. And one of my conclusions will be that we really need to kind of trust the reanalyses, or in deference to An and Patrick, the state estimates, because I really think that the statistical objective analyses just don't work very well in the Arctic. This is 100-meter temperature. This is my second to last slide. Upper panel shows climatological temperature in the 0 to 100 meters. The lower panel shows the trend. This is just a linear least squares trend computed over the full 41-year record. And I'm showing this simply to make the point that you can see this really dramatic warming of the northern Nordic seas extending into the Barents Sea. And it shows up in all three products. It shows up in the new rare, it showed up in SOTA 3, and it's in EN4 as well. And it's really, really striking. And this is my last slide. I know there's another part of this organization that's interested in the influence of the subpolar gyres on the Arctic. So I thought I'd take a look at the regression relationship between temperatures inflowing into the Nordic seas here in this green box, that's Iceland right there, and the annually average temperatures throughout the Nordic seas and the Barents Sea. And the left-hand panel shows the regression at 0-year lag, the middle panel 1-year lag, and right-hand panel 2-year lag. And if you look at this a little bit, by the way, the time series is the one in red here. And if you look at this a little while, I think you can convince yourself that you can see this northward progression of the anomalies from the Atlantic subpolar gyre through the Nordic seas and even into the Barents Sea. And it actually also shows up qualitatively speaking in all three products. And so with that, I'll just give you my challenges and directions. Challenges, so I'm convinced after producing rare and previously producing SOTA that we really need higher resolution if we're going to do the Arctic problem correctly. And I'm convinced that the target resolution should really be something like between 1 and 3 kilometers horizontal and roughly 1 meter resolution vertical in order to be able to describe the key scales of motion. That includes the deformation radius, but it's not only the deformation radius, it's also, for example, these very intense boundary currents. Mixing is an issue which we have not addressed at all. And of course, there is this substantial inconsistency between the surface fluxes and what I believe the Arctic ocean, dynamical ocean models expect. So I think there's a big bias issue there. And in terms of future directions, I just want to let you know that we've stopped Rare 1. So we've produced Rare 1, but we're actually trying to develop its successor now. And its successor will have this 1 to 3 kilometer sort of target resolution. So that's really what we're working on right now. And with that, I'll stop.
Thanks very much, Jim. We have some time for some questions. If anyone would like to unmute and ask a question.
Jim, this is Subra.
Hey, how are you doing?
I'm doing fine, thank you. It's a nice talk. So I have 2 questions. So recently we did the comparison with the different models like HICOM, ECHO, and Glorious 12 and Virus 5 with the mismatch. So we compared in the Beaufort gyre region. So finally, we found that the ORAs 5 is doing much better in the Beaufort gyre region. I will send you that paper. So my question to you is, have you looked at how different ORAs 5 with this rare one?
I haven't. So I compared ORAS 5 to SOTA 3 in the Arctic.
Mhm.
ORAS-5 has the same 75 vertical levels that we chose in rare. And the reason why we chose them in rare is that I also liked ORAS-5.
Mm.
But ORAS-5 has the same horizontal resolution as SOTA-3. And I think that that is a handicap. So it does okay with the freshwater storage in the buffer gyre, which I think is the problem you're thinking about.
Right.
But I guess that if you took a look at some of these other features like these shelf currents and so forth, they are not going to be all that well represented in ORAS-5.
Okay.
So just to recap, so ORAS-5 uses ERA forcing, so same forcing. It uses quite similar data, except that they also include sea level. It uses quite similar data assimilation, but it has more coarse horizontal resolution.
So the second quick question is this rare one is available publicly?
Right, so we've got a manuscript, and I figured I'd wait until we actually get the manuscript submitted, but I have the manuscript sitting on my table here, and I hope to get it out of here within the week. As soon as that's available, we'll make all the, we've got all the SOTA data sets ready to go, and they'll go on our sota.umd.edu website, and you can download them. It's all, the usual NetCDF.
Great, thank you.
Sure.
Thanks. Jim, just quickly, how again are you using biomass?
Oh, so yeah, I didn't really have a chance to explain that. So what we do is we modify the net surface heat flux hitting the top of the ocean sea ice system proportional to the difference between the forecast sea ice and the biomass sea ice. And that's a long way of saying that if we have too much sea ice, we add more downwelling heat, atmospheric heat. If we have too little sea ice, we extract atmospheric heat. In other words, we don't heat as much.
You're tuning the energy. You're tuning the energy budget to give you biomass thickness.
Exactly.
Yeah.
And so we let the ice model do all the dividing up snow and ice by categories. We let the ice model do all the tracking of fresh water and so forth, so we don't have to worry about making sure that fresh water adds up, right? So that's how we do it.
Okay, let's go to Wilbert quickly.
Yeah, one quick question. You may have mentioned it, but what do you prescribe on the boundaries of the domain?
Oh, we get those. They're effectively the same as SOTA-3 at 45 north.
Okay.
In fact, a lot of our troubles were fooling around with the boundaries, frankly.
Mm-hmm. So you're using the SOTA reanalysis to force this high resolution rare reanalysis. Yeah,
in effect, and the resolution increases until you get to about 60 north. So it would, so it doesn't really get, so we don't really want to look too much at the subpolar gyres because I don't even think they may be that great. We really want to look, once you start approaching the southern tip of Greenland, once you get into the Bering Sea, places like that, we really have the resolution.
Great, thank you.
Okay, thanks. Let's now hear from our second speaker. Nguyen is a senior research scientist with the Odin Institute for Computational Engineering and Sciences at the University of Texas at Austin. And she'll be speaking about the Arctic Subpolar Gyre State Estimate.
Thank you. Richard, just give me a split second to share my screen here. This. And this. Yeah, you see okay?
That's good. Yep.
All right. Thank you very much for including us, and so that we can see some of the other exciting products, as well as also introducing the community to our products. I will talk about the Arctic Subpolar Gyre State Estimate. as a data model synthesis, as well as a tool for Arctic climate research. And this is the work we've been doing both at UT Austin with my colleagues here, as well as ECHO colleagues, because the ASTE used an extensive amount of tools developed within the ECHO consortium for doing state estimation. And we've distributed the release 1 of the product both at the Arctic data.io from NSF site, as well as Mirror on our university site. And there was a manuscript in 2021, so last year, that described quite extensively the assessment of the solution, at least to our ability, because we know that there are many regions and interests, and a lot of it might not have been looked at. And so the first slide will give you somewhat of a configuration description. The one on the upper right corner shows the model configuration. And the goal of the project, originally it was an NSF funded project, was to understand the time mean and time varying ocean sea ice states in the Arctic and subpolar gyre. And we set the configuration as far south as we could afford in order to avoid potential problem with open boundaries. And that's why it was set quite far south there. And the initial conditions was spun up from the World Ocean Atlas 13 version 1, which was not including ITP data at that time, because we started this project some time ago. But I noted there that it was then subsequently adjusted as part of our estimation, which I go into detail a bit later. And the CIs was spun up from the Polar Science Center estimation biomass for January of 2002. The forcing was from gyre 55, adjusted again. And then I want to make a mention here from my experience doing high latitude modeling, that some of the biases in the reanalysis products obviously will have large consequences in what we do, as Jim mentioned. And it was based on my experience, it was found that gyre 55 had the least of the bias important for what we do, and that's why we ended up staying with that product rather than the ERA interim and subsequent products. And the open boundaries were extracted from the global 1 degree ECHO version 4 latest state estimate at the time, so that was release 3. And the control variables are the parameter space that we estimate in order to improve the solution and reduce the model data misfits. And these include internal model mixing parameters such as the horizontal eddy stirrings and the diapinal diffusivity in the vertical, as well as the initial conditions for the hydrography and the time dependent or time varying atmospheric forcings, the fields from gyre 55. And the resolution is approximately 13 kilometers in the Arctic. And this was a compromise due to the fact that we are doing quite expensive calculations, which I go into detail perhaps in the next slide. And the optimization period, we had to make quite a few considerations. Originally, we would have liked to go all the way back to the beginning of the satellite period, but it was quickly realized that the state estimation is severely constrained by the availability of the data. And so as we have found out, and probably the community, the people who do data assimilation, they would find out, when you don't have observations, then a lot of the time it is just a model unconstrained run, even though you try to backtrack all the way to initial condition improvement. And so the choice we ended up with was 2002 to begin, which coincides with the beginning of the GRACE and ISAT-1 missions at that time, close to the full Argo deployment period of 2002 in order to get the improvement in the low latitudes, the North Atlantic and the subpolar gyre regions, as well as the beginning of the ITP deployment period, beginning in 2004 or so. And So the primary data constraints include the entire suite of data that the standard ECHO state estimation, global state estimation use for the low latitudes. And we supplement it with some target data sets for high latitudes, including but not fully comprehensive here, but including the sea ice concentration daily, the sea ice thickness and sea ice drifts at monthly temporal frequency, and hydrographic sections and more data from the various observational campaigns, as well as at the important Arctic main gateways. And I want to cover the methodology very quick, just to also explain the difference, because Jim had mentioned that earlier as well, the difference between how we approach doing the estimation. So we use the 40 var with a very long assimilation windows of 16 years as the approach. And typically what this entails is you develop a functional form of a data model misfit, which is sort of depicting here with a J prime function. The first row essentially just captures all of the data model misfit through the entire time spanning of the model run. And then the second row, sort of a typical example of any a priori additional information that you can have that can also constrain the solution. And then the third row is the important difference likely between what we do in general versus sequential or versus 3D VAR estimation, which is we use the Lagrange multiplier method to constrain the model physics strictly to obey the momentum and tracer conservation laws. And so by doing so, we want to, the reason is we want to maintain such that all sources and sinks in the model is accounted for when we strictly obey the physics. And so what that entails, here I give an example, the techniques that one use to do data assimilation, then often is based on the objectives, the science objectives of what we would like to do. So for example, if we were to do short-term forecasting or with short data assimilation windows, for example, that would be depicted by, for example, the black trajectory shown here, where you have the trajectory coming in, and then whenever you have a data being introduced, which is depicting by the triangle, gray triangle here, you would have, as Jim has shown, you then can have an incremental so that the model can then match with the observations and reduce the misfits. And potentially one can also, in the end, after you finish all of the trajectory, you can actually run one last pass to smooth out these jumps. But one of the key things here is still that regardless of the approach there, you can or most likely violate the conservation laws, obviously, because you introduce sources and sinks that can potentially you cannot fully account it for. And that was at least our approach. We would like to avoid doing that because we would like to use the product for a different sort of reason, which is to do climate research, where we want to maintain strictly the dynamical consistency and be able to close the budgets. And that has obviously drawbacks. Obviously, it has the advantage of being able to do budget analysis and look at trends, etc. But it does come at the expense, for example, where the full model trajectory then cannot always match with the observations because it is fully constrained by the model physics. And so we use the model, the fluid dynamics equations as the constraint for the trajectory. And so the next two slides, I simply show some of the examples of the constraints or the misfit reductions of the product. And again, I would encourage people interested to also take a look at the very detailed manuscript where we show assessment, but this is just an example. For example, typically we assess the solution by looking at the reduction of the normalized misfit square here for the various data products, both if we use them as for post analysis validation or during the procedure for minimization as well. And I just zoom into one example here for the sea ice concentration example, where on the left here, it's shown for various regions, because we typically also want to understand whether we have a reduction change in sea ice marginal ice zone versus the multiple year ice distribution. And what's shown is on the left bars here, the misfit. Sorry if I can find my mouse. The misfit for the unconstrained solution, where potentially you can have a lot of bias due to model spin up and etc. biases in the inputs. And the state estimate was able to reduce for all of the regions. And an example here shown for the GINSEA, where the data from the OCSAF is shown in black. And it's just an example of the original bias from, you know, errors in the ocean, the hydrography, the flow, the model drift, etc. that for that particular case produce an excess amount of sea ice. And we were able to have the reduction of that. And I show one more example of the reduction, in this case for ITP data. This example only for temperature in the Canada Basin. And this is as a function of depth going down to 800 meters in the water column. And this is normalized misfit of model minus data normalized by some uncertainty that we quantify for the typical data and model representation error. And the unconstrained solution has some large bias, and you will always have these kind of biases when you run an unconstrained solution due to the various issues. And it shows it has a very large warm bias and very large tail, for example. And in the constrained solution, the first thing we notice is obviously that we have now managed to get a very large distribution now centered around zero. So the reduction is significant. And the tails are also significantly reduced here. So I only show very limited assessments here because it's in the manuscript, but what I want to highlight, hopefully in the next 2 slides, is an understanding of what misfit reductions mean depending on the techniques you use and why they are important for understanding and what you want to use the solutions for. So I again copy the misfit for the optimized solution here. And I also draw the blue line where the zero misfit is, and that's essentially what you want to achieve within the plus minus uncertainty bound. And I also draw a box here of the red box here that shows typically the technique you use, you might still, for example, in our case, the product still has quite a persistent bias. And this has to do a lot with the model systematic errors or things that we don't have the parameterization to actually have yet the improvement for, and that is something that needs to be continuously developed and improved on. But some of the questions that we are often being asked is that if there's so much extensive amount of data, why can't the model fit with the observations in the regions where we have the data? And I think I try to allude to that already when we explained the method, being that we want to constrain to the model physics. But more importantly, I want to highlight also that there are different techniques that you can use to get the solution to match the observations. But then we have to understand sometimes a good fit does not guarantee the dynamical consistency if that's what we try to obtain in order to understand the changes. And I provide here an example of, I just took one profile in the Canada Basin, and that's the dark black curve here with the dash black showing the uncertainty of that data. This is only for one profile. And the there's two groups of data sets here. One is just the outdated climatology, showing that there's always still a bias, a cold bias from the previous period that has not been captured in the climatology. And then the new set of climatology shown here, the latest World Ocean Atlases products that actually incorporate ITP in already, and therefore it actually achieves a very good fit to the ITP data. And also ASTE is shown here. But what I want to highlight is when we do have the data, then you can actually compare them. But the question perhaps we need to understand is for the Arctic, where the data distribution is quite limited, that what will happen where at the places where you don't have the data, if the technique you used in order to get the data to match is only available at the time you have the data. So I show here an example of the distribution of the ITP profile in log 10 counts of the number of observations, with also hand-drawn profile of, hand-drawn depicting the consensus understanding of the flow of the Atlantic inflow, for example, into the Arctic. And so just a different visualization to show that most of the observation was obtained in the interior basin of the Canada. And there's quite a lack of observation along the path to constrain the flow coming in. And therefore, at places where we don't have the observation, we require to have an interpolator of some kind in order to get the solution. And so depending on the products, we can have an interpolation that at least we know obey the model physics, or in some cases, if we do the kind of matching, let's say, where we do incremental assimilation, or we use different techniques, that you can end up incurring some kind of jump. So this is an example for one of the products, ocean reanalysis, for example, where you have data, you can actually achieve some good fit. And where you don't have data, you can incur spatial or temporal trends, etc. So the next couple of slides are simple, just the kind of assessments that we can do with the solution with dynamical consistencies. So this one in the paper just show the budgets for volume fluxes, for example, and the same can be done for heat and fresh water. And because we understand the sources and sinks, it allows us then to be able to look at the whole time series and understand where the source of heat change, for example, coming from, or heat loss, or freshwater gain and loss. So these are just two examples of the upper ocean Barents Sea heat content or the halocline heat content in the Western Arctic compared to some other observational based estimates for trying to understand changes in the Arctic. So I just give a quick summary that ASTE at the medium resolution was constrained to more than 1 billion satellite and in situ observations for the entire period. And the method used a strict adherence to conservation laws, and that allows us to account for all the sources and sinks, and therefore at least we know we can use the solution to understand changes and try to close budgets. And the ASTE captures the large-scale dynamics of the ocean sea ice system, including variability and trends. That one was in the paper, but obviously it also has a lot of outstanding, still remaining systematic biases relevant, for example, to what Jim mentions related to resolution or the model systematic biases that we still need to keep working on, trying to understand the parameterization and therefore improve the estimation. Thank you very much.
Thanks very much, Anne. Do you understand these observation misfits to be just a sampling issue, or is there something systematic associated with the observations? And I guess the thing that came to mind for me was with the ITP. We've had a discussion in our office about whether to use them all the way to the top of the water column, or if there's going to be a mismatch with the sea ice model. Do you have any thoughts on that?
I think if we can focus first on what we can observe, rather than worry about what the mismatch might be to the models, because the models, we develop some understanding of physics, right? But we understand that the physics iteratively be improved with the observation that can validate, let's say, a process studies. And then after that, you can try to then scale to a different resolution where we understand if we don't capture the full dynamics, then we need a parameterization that can actually try to capture the process. So I think I'm not sure if I worry yet about models when we try to obtain something that can quantify the physical process. And for the ITP, for example, I think if we can get it to the surface, then we have better constraint of the upper ocean compared to, for example, we know the model has issues with upper ocean mixed layer depths and mixed layer processes in general, right? And because we don't have a good constraint for the fluxes. And we should also understand the reanalysis for the atmosphere, for example. They also have a severe lacking of observations in their reanalysis. And so most of the time in the high latitudes, a lot of the reanalysis for the atmosphere that we get, those are actually just forward model runs, because they don't have the observations, or they also have biases in themselves as well. So a lot of that, if we feed it to an uncoupled ocean sea ice model, then we also need to understand that we are feeding data boundary conditions with also uncertainties that we need to account for example. And I just want to touch base again on not particularly, related to ITP. That ITP was absolutely critical for us to improve the interior ocean of the Arctic. But perhaps we can also try to have the system somehow mimicking also perhaps Argo, where it can drift along with the ocean currents, because then it allows us to have additional constraints of the information that we are lacking upstream where the important water mass enters, because this info is so further downstreams that if we think of it in terms of an inversion problem, you have so many pathways potentially by the time you arrive at downstream solutions. And so the upstream information is so under constraint that it can definitely have impacts. You don't have enough pathways because it's so non-unique and so underdetermined. So that's
Richard,
one of the problems you end up. Yeah,
Richard, it's a little disconcerting to hear you guys are thinking about throwing away the upper part of the ITP data, since we've been struggling and actually are able to now sample all the way up within like 10 centimeters of the ice-ocean interface.
Oh, wow.
Because in summer, there's a 50 centimeter thick surface mix layer with water melting.
John, this is so interesting because, we've been producing these mixed layer pictures and I was wondering, what it actually looks like. So I'd love to have you sort of give me a reference or
so
educate me.
The new instrument's called TOP, Tethered Ocean Profiler, and it gets all the way up to the ice-ocean interface. And we have a few of those out now, and we'll be putting more out. And it may be ITP2 that may be coming down the road. Well, all of them will do this now.
Because I suspected it was really shallow, under the ice, right?
Right, in summer.
Yeah.
Hazel is telling me that I should mention that we'll be going along here. So we're approaching the top of the hour if you need to go to something else, but we'll be continuing this discussion here. Supermayor, I see you have your hand raised.
Yeah. Hi, Anne. How are you? You gave a nice talk. I have a very quick question. So you're using echo as a boundary conditions for your estimates. So in our comparison with echo salinities are a little bit saltier at the surface. So how good your salinities are, and how have you compared with the satellite Delavar salinity? Is there any mismatch between your model and echo or satellite Delavar salinity?
I think obviously there will always be mismatch.
Right.
But so maybe the first thing I mentioned is the echo solution at the open boundaries did not end up impacting our solution a lot, simply because we took the precaution to move it as far away from the from the solution as possible. So in our case, it's in the Bering Sea where the solution, the water would need to transit the Bering Sea through the Aleutian Island in order to finally make it to the shallow shelf into the Arctic through the Bering Strait. And then in the southern tip of Africa was where I put my, there were open boundaries. So that is not as critical, but what is critical, and I think Jim mentioned that as well, is the constraints for freshwater fluxes for our estimates, whichever approach you do, but river runoff. And I think I had talked to John Toole, and he, John, you mentioned also colleagues at Hui who had also done some research now improving, but that is our biggest constraint or lack of observations. And if you don't have the freshwater fluxes, then you are up to trying to make some kind of estimates, for example, right? You could try to take, for example, from gyre 55, do they release, or ERA interim, which, and all of those are, again, model outputs of some kind, right? They can try to constrain with observations, but if the observations are lacking, all of those are essentially just forward solutions. So
and
then,
what do you use for river runoff?
so we had been using something quite outdated, but it's from Fikete, and this is a product, sort of, it's a assembled product of climatology only. So it's 12 months climatology only, and part of the adjustments we can do is to make adjustment for runoff, for example. But given that we don't know well the uncertainty, and the changes in the 2000s. So then you are up to essentially, if you want, you can conduct sensitivity studies where you can change the freshwater by some amount. And in the adjoint framework, you could actually then also use the adjoint to propagate backward to see upstream where the information would impact the particular misfit for salinity, for example, in the solution. So to answer your question, Supra, we know that we do have biases, and I think in the Arctic we have a salty bias in ASTE that we know of, and the release one at that time actually we didn't have the sea ice adjoint working correctly, and now we have a fully adjoint sea ice working, and that would allow us, if we have data, we can then now constrain to the process of exchange with feedback to the sea ice, and hopefully with that we can improve the concentration of salinity in the upper ocean. But the river runoff is still a really big challenge for us to have some good estimates in order to force the model.
Wilbert?
Yeah, very nice talk, and very impressive work. The great thing about your approach is that you can fiddle a little bit with the physics, right? In the model. What did you learn about vertical mixing in the Arctic basin while you were doing the optimization?
So I think we worked quite a bit with John in this original joint project, and one of the things I realized is actually mixing in the Arctic is really a difficult problem because of the halocline. So we don't have constraints of mixing. What we have is constraints based on TS profiles, from which we can then, if we want, we can convert it to density profiles. And from there, we can try to constrain. But at the same time, if you don't have a good error estimate or how well you can constrain. So you can imagine we start with an initial guess of mixing, and then we would like to improve on it. But the problem is if you don't have good constraints on the uncertainty of the parameter vertical mixing, and this has to be fully 3D, obviously. It can, unless we want to only use a single number for the entire basin, which we know is inappropriate. So the uncertainty also implies that you can make an adjustment within the uncertainty, right, in order to improve the solution. But if you don't have a good estimate of the uncertainty, then the adjustment can be as big as that, And if it doesn't actually capture well the physics, then you end up actually over mixing or under mixing. And we found out it will halocline is so sensitive to the understanding of mixing that any slight change, because once you have it, then the model will now constantly be using that, over the time scale of the model run. And pretty much most of the approaches that we have tried degrades the solution very quickly. And so in the end, what I had done was I tried to gather from the literature sort of limited estimates. For example, we know in the interior of the basin, double diffusion is dominating, meaning turbulent mixing is quite minimal. So then we reduced that number to be very small. Let's say 10 to the minus 6, 10 to the minus 7 to account for numerical mixing. And then the question is now, how do you assign the uncertainty there, right? And then we have an understanding that as you approach the topography, we know that there are enhanced turbulent mixing because the staircases are being destroyed. So then you can try to scale up, for example, the first guess of your 3D field over there to be of certain range. And then we know the water column has a particular structure for the halocline. So therefore we can try to understand where you would expect, because for example, a gradient and anything can induce a lot of mixing if the diffusion coefficient is high or low. So as you can see already starting out, we try to gather the literature as much as we can, but the uncertainty are so we just don't have enough information. And therefore, even if you try to optimize in that sense, and then you have to balance between that versus now the horizontal eddy stirring. So let's say we know the eddies distribution, from Mary Louise work, for example, that we know some kind of distribution of eddies. So therefore, we might try to understand what kind of range you make as your initial guess for the horizontal stirring. But then now you have a competing process that is also as under constraint because it's again some initial guess. So when you try to make the next the reduction of the misfit, now you have a non-unique pathways to change the solution. You can either try to improve horizontal or vertical mixing or initial conditions or hydrography, of some types, etc. So there are multiple pathways, and for an unconstrained problem that can be quite difficult, because then you will find out, okay, sometimes you have to withhold one parameter set in order to see how sensitive it is to another parameter set. You can argue whether physics should have already accounted for that. And the uncertainty, the way you set up the problem should have accounted for it to know which pathway, but not necessarily when you don't have enough data, right? Because an inversion problem with under constraint, with an undetermined sets will give you always quite a number of pathways you can choose from. And so based on that, during the time we were reducing the misfits, at some point we had to make a decision to even remove the vertical mixing from the estimation, because I think if it tries to match the vertical stratification, obviously that's one way it can try to do it. But then in short term, it will do that. But vertical mixing obviously operates at the diffusion time scale, which is longer time. And therefore, actually, in the long term, you find out that, well, longer than the eddy stirring, I think, and the advective scale.
Because another wrinkle to this is vertical resolution of the model does
That's
depend
right.
for the vertical diffusion in particular. And I noticed your misfit plot for the Canada Basin showed a big spike at the depth of the Pacific summer water. ASTE is presently underestimating the warming. And I think it's because ASTE is too diffusive.
It is very possible that it is, and generally, I agree with you that it is too diffusive just because of the vertical resolution. But at the same time, we also understand that mixing is an episodic event sometimes, right? It depends when you put in the forcing, that's when you actually can have episodic. It's not a time mean. And yet at the same time in the parameterization, maybe we cannot fully afford fully 3D field time evolving. Even a seasonal cycle could improve, for example. So at the moment, what we have is a single time constant. Is changing in 3D, but it's a time constant. So now you are trying to approximate the physics slightly different than what you can fully capture. So as you can see, there's just so much that development could try to improve, for example, because if we go with, I agree with Jim, high resolution can capture a lot of info, but at the same time, it will also introduce more problems. As you know, you can change the solution to any resolution. You will find there will always be processes that you haven't thought about that is suddenly now, for example, pop up that you don't have the dissipation for example, what if your current boundary currents are now too energetic? How do you account for now dissipation of that energy? Because then it's another field that you have to work with. And the higher resolution you go, the more grid boxes, the more unknown parameters now you would try to estimate, for example. So it's always a difficult.
Jim, do you want to respond to that?
Respond sounds like we're in a debate here, but I really, I've been staring at these pictures for the last month and looking at SOTA, which is this coarser resolution, and I really am convinced that that what's the deformation radius is something like 10 kilometers in the deep basin, and it gets down to like 1 kilometer up on the shelves. And as John points out, the vertical resolution, if you get that melting at the base of the sea ice, you get those, high salinity gradients very close to the base of the sea ice. I really think that resolution is an issue that we got to confront. I'm sorry, because I realize it poses a huge computational burden, taking your approach, but I do think it's something that we got to somehow find our way to, frankly.
No, I do agree with you that it's very obvious that if we try to get a blur picture of the Arctic and think somehow we can capture the by having low resolution is what I meant, and then try to capture
Like
the process.
How do you do frame straight at low resolution? I just hurts.
You mean frame straight? At least the frame straight has enough certain, but but you are right. The Nordic Sea even has shorter baroclinic deformation radius because of the dynamics, the topographies there. I completely agree. So I think it's going to be a balance between the two. And for example, even with our approach right now, we are working on improving the resolution to 1 meter actually in the upper ocean, as well as 4 times higher resolution. And we are working on sort of like a multi-grid approach, like the atmospheric reanalysis. That's what they do as well, where they know they cannot fully resolve the whole process at high resolution. So some of the analysis that they do is actually at a different resolution and physics, and then
like a super parameterization kind of thing.
Kind of, but I think in the ERA, ECMWF, how they do it is sometimes they run the model at low res in order to reduce certain type of misfits that are more large scale, for example. And then once they improve that in the forward run, then they actually used it for the analysis, a different resolution, taking into account that increment that they derive from the lower res. So, yeah.
Mike, do you have a question?
Yeah, Jim, I mean, so you've done SOTA for a while, and you're comparing right now, today you're comparing rare and the latest SOTA, then there was like a crappier SOTA before that. And I mean, are we, what I'm asking is, are we asymptoting towards reality? Like if you compared rare with the SOTA you showed us, and then like some, older SOTA, and then an older SOTA, are we like getting, I mean, obviously we're improving with resolution. That's almost like, I mean, I'm not surprised, I guess, but is it asymptoting to something, or?
Okay, so this again is just Jim Carton's opinion, and actually we have Julie McLean here, who's, I mean, this is her thing, this high resolution stuff. But in my opinion, there is a critical horizontal and vertical scale in here, or range of scales that we kind of got to hit. It's a mark we got to hit. And I think that like the deformation scale is a horizontal scale we got to hit, because otherwise you're just not even doing baroclinic instability processes right. And in the vertical, I'm guessing that people who know about, these vertical processes, maybe John can tell us that there probably is some, quite shallow vertical scale that you kind of got to get. Otherwise, you're just going to miss some basic processes going on in the, say, summertime mixed layer under the ice. So I think it's not a continuum. There really are zones that you got to hit in order to be able to sort of get to a certain quality, my opinion.
Maybe I can add a little bit to that as well, because like Jim, I think we have been doing a lot of, you change the resolution as your computational resources improved. And we have actually found out that you will reach an improvement, continuous improvement, but then at some point actually it becomes a degradation. And this has to do with there are certain resolution or certain regions that a particular grid model represents well the deformation, for example, or the process is there. So such that you can actually have about the right strength of boundary currents or the right exchanges. And once you go higher resolution, now you capture different processes because you have more eddies, you have more activities. But now, as I alluded to earlier, then suddenly there are different dissipation processes you haven't thought of yet that are now required for you to dap some of that energy away, or to understand how to map that energy to the main flow, for example, because now you've got eddies that might actually be detrimental to your boundary, your mean flow. So just because of the parameters, so the resolutions actually does have, we can always increase them. And we have found, for example, the core Atlantic water in the Arctic, you can increase them, and at some point you end up capturing the sea ice edge just very well for the same forcing. You don't even need to make any adjustments, or you get the boundary current to just have the consensus strength and circulation, for example. And now you can keep changing, and suddenly you can have now a much stronger Arctic inflow, Atlantic water inflow, and you end up warming the Arctic significantly just because the change of the strength. And now you are back to the problem, how do I adjust for whatever that I had prior in order to get the solution there? So higher resolution with an understanding of processes is very helpful, because then we can understand what processes, what are the competing factors that could be potentially that we need to balance for. But if we don't have that understanding, so I think the community, for example, for the longest time, at the time when Arctic resolution, Arctic modeling resolution was increasing, I remember it was a big problem where suddenly now we have excess of Atlantic water heat into the Arctic just because the boundary currents are now a lot stronger. But nobody could figure out how to reduce that strength, for example. Never mind the other problem that the circulation reversed because of the low sensitivity to change of F in the high latitudes that can give you multiple pathway for you to have the same vertical profile of T and S fit.
So Jim's rare is now at 1 to 3 kilometers and 1 meter. Yeah.
Will be.
Okay.
Will be. Yeah, we're trying to get down to 1 kilometer horizontal. We're already at 1 meter, at the surface, but it telescopes. It's the ORAS 5 grid.
So what Anne is telling you, Jim, is that you may screw things up. We'll see. That'd be interesting, huh?
Typical. It's typical of Carton.
No, but I think we should not be afraid of that. But what we should understand is if we have a systematic approach for reduction of misfit, because I still remember my introduction to modeling in the Arctic. I'm sorry to say this, at the AOMIP meeting a long time ago when I first got introduced to this, was a conversation that someone said, I changed the model and somehow it fixed this thing in the Arctic. And now we don't dare to touch anything anymore, because if we touch it, it will change and we don't know how to fix. And I think that's hopefully not the approach we would like to do, because we want to understand processes and hopefully a systematic approach. So I now at least know that things will change when you introduce new physics, because you have tuned the system to to maybe not sufficient physics before, but it should not prevent you from having the improved physics as long as you understand a systematic approach. And that's always the difficulty, that we think we understand until when we approach it, and then, okay, the solution is degrading. So do we really understand it,
On that positive note, it's 20 minutes after the hour. I think maybe we should draw this meeting to a close, but I would again like to thank Jim and Anne for their presentations and the wonderful discussion by everyone who's joined us. Wilbert, do we have any other comments to add?
Not that I'm aware of, no.
Okay. I noticed in the announcements, there's a US CLIVAR workshop in Seattle on Arctic ocean circulation next week. We are still working on our meeting for next month. And I think that's it.
Thanks so much,
everyone.
guys. This is educational for me, so it's
Yeah.
great.
Thank you very much.
Nice to see you.
Great meeting, absolutely.
Thanks very much. Okay, bye-bye.
Thanks, everyone.